So did they give you any, like when they were announcing it, did they say any background about the cup, about the history of it? So I'll tell you a little bit of background. So if you look, actually if you look at the cup, we had won the competition about 10 years ago, but the cup had, I think this was the first time the cup left the state of West Virginia. Is that what they said?
I don't know, they didn't say anything.
So a little background, the Hardy Cross competition goes back decades, right? And, but the cup, the actual trophy, had to stay in Virginia, right? Because Hardy Cross, that's where he was originally from. So if a student in West Virginia won it, but we got like a little trophy, but the cup went back to like the host school or whatever, right? So about 7 or 8 years ago, the conference got together and bought a new cup that could travel because the rules said the cup had to stay. So they retired that cup, and I think it's like at Old Dominion right now. And I think so this is the first time that cup has actually traveled outside of Virginia. So good job, sir. So now we have to find a place to appropriately protect it. Like I said, we've got our display case, but so in all honesty, we might actually like get a display case for it. I don't know. We've actually had some preliminary discussions about that this morning because it's heavy. I am a little concerned about putting it in the one in the hall because of those little glass shelves. It's big. It might not actually even fit this way, you know.
It's maybe too deep.
It's big, you know.
It is big. I don't know why Josh isn't drinking out of it right now.
No.
What?
No. No.
Well, the lady, when I went up there, she said, just if you're going to post on social media doing that, just post it on Snapchat so it goes away.
Hey.
Was that Christina that said that?
I don't know.
Just remember that this lecture is being brought to you by Raid Shadow Legends. Just remember that. So, no, none of that. Okay. Because of just the festivities this weekend, I was working on the exam, but I just didn't finish it. So, my goal is to get it to you this week. I'll admit that I also have back-to-back advising appointments for everybody that signed up for advising. So I'm a little back-to-back on that this week. I decided because of the festivities to go ahead and extend Homework 5.4 to Wednesday. Also, I wanted to see if anybody had any questions about Homework 5.4. Okay, all right. So that the reason I mentioned is that's our last column assignment in this class, and that's our last column exercise. So in terms of what the rest of the semester is, we have the most important topic, which we're going to spend about 3 weeks on, which is beams. Okay, we haven't really discussed beams yet, bending, and that's going to be the main topic of discussion for the rest of the semester. But we do have one lecture that we're going to devote to local buckling, because we've sort of sidestepped that, and we kind of need to take a step back after beams and discuss local buckling. And then at the very end, I want to try, and this is going to be a little bit of a new topic this semester, but I want to try and tie everything together and look at applications. So, for example, if I give you a problem and I say the dead load is this and the live load is this and the snow load is this, well, where did that come from? Like, did I just come up with those numbers out of the sky? Well, no, there's a process to determine those loads, and they are related to the building application itself. So I want to see about maybe getting some snow loads for buildings, talking about live load reduction, some other building related aspects to sort of tie it all together. But today we're going to begin our discussion on beams. So before I jump away, did everybody get the code? Okay. I distracted everybody with discussions of trophies and whatnot. But yeah, again, congratulations to our team who did very well. Had one of the most memorable canoe races in conference history. That was amazing. Everybody in the crowd was like, well, you don't see that every day.
That was spirit of the competition, right? Wouldn't you say that?
We should have got spirit of competition.
We didn't?
No, they gave it to the high school
guy.
Oh, well, okay, they gave it to the high schoolers.
They give it to them every year.
They gave it to us.
Okay, all right. So I won't mention the other school because, again, this video is being brought to you by Raid Shadow Legends since we're being recorded. But our canoe, it was having a rough day. It was taking on a little bit of water, and it was our women's sprint. I think it was. It was the women's sprint, and our canoe was sinking so much so that the only thing that you could see were the little floaty pool noodles on the side. I mean, like, here's the water and here's the top of the canoe. And our two girls who were racing, they were giving it their all, and they actually beat the other team with the canoe under the water. So, yeah. So unfortunately, it like as the competition progressed, it turned into more hole than canoe. But the team did an absolutely fantastic job, and they had y'all had a ton of grit. So I'm very proud of you. Okay, now let's talk about beams. Okay, so I want to take a step back and let's go to. So I'm gonna tie together two courses that you've had in college. So one of them being structural analysis, right? That's what y'all had last semester with me. So the idea is, okay, if I give you a beam, right? Let's say it's a simply supported beam. Let's put a uniformly distributed load on it. You all can calculate reactions, draw shear diagrams, draw moment diagrams, etc. Right? And so if I were to show you a diagram like this, I'm hoping that it would at least be somewhat familiar at this point, right? So for the purposes of design, we are typically interested in the highest moment at that moment diagram. That's not to say that's always the case, but in most instances that's the case. We are actually going to talk about a couple instances where we need moments besides the moment right here, like we need moments in this part of the span. But I'm running before I walk at that point. Let's take our time with that. Now this is what we learned last semester from structural analysis, but I also want to tie together the stuff that you learned in Engineering 216, mechanics of deformable bodies. So I'm hoping that this formula right here is fairly familiar, the idea that sigma equals my over I. So what that basically means is that if I have a given cross-section, right? So if I have, let's say, an I shape, or if it's a triangle, whatever, it doesn't really matter. But if I have a beam with a cross-section that, let's say, looks like this, from this cross-section I can compute both the location of the centroid and I can compute a moment of inertia. Remember, the moment of inertia is just a numerical section property that indicates how stiff the section is in response to bending, right? So the idea is that the higher the moment of inertia, the lower your bending stresses are. And that comes from this, right? So as the I gets bigger in the denominator, this gets smaller, right? So what it also tells us is that bending stresses are essentially zero where the centroid is, and as you get further away from the centroid, the bending stresses increase, right? Either in compression or tension, right? You probably heard the phrase like smiley face positive, frowny face negative. So if the beam smiles at you, it means the top's in compression, the bottom's in tension. We refer to that as positive bending, right? Everybody with me so far? I'm not speaking, way out of turn. Everybody knows what I'm talking about. Okay. All right. So let's dig a little bit more into Engineering 216 land. And a lot of what I'm doing right now is both a refresher of concepts that you should have seen before, but I am also introducing you to some notation, okay? For example, the moment of inertia. We have a moment of inertia about the x-axis and about the y-axis, depending upon which way we bend the cross-section, just like we have a radius of gyration about the x-axis and the y-axis. We have an r sub x and an r sub y, just like we have an I sub x and an I sub y. We also have an s sub x and an s sub y. So what's the deal with the section modulus, or this term s? Okay. Well, if sigma equals my over I mean the term sigma equals my over I, that expression will tell us the bending stress at any arbitrary point along the depth of the cross-section. But if the bending stresses are zero at the centroid and they're maximum at the top and the bottom, and it's linear, we don't often care so much about the bending stress right here or here or here. Really what we care about is the bending stress either at the very, very, very tippy top or the very, very bottom, okay? I'm not saying that's always the case. Sometimes we do care about bending stresses there in the middle. There are some very clear examples of that in various applications in bridge engineering. For example, if you're looking at welds at certain depths and things like that. But usually all we care about are the maximum stresses at what we call the extreme fibers, either the very, very top or the very, very bottom. Now, if sigma equals my over I, but our extreme fibers are at the very top and the very bottom, typically what we'll do is we'll define this term C as being our extreme fiber distance, C being the distance from the centroid either to the very top or the very bottom, those extreme fibers. And then we'll say, okay, if I take sigma equals my over I, and I take the term y, and I replace it with this extreme fiber distance, basically what I'm doing is I'm taking a moment, but this term right here is just another section property. And if I put it on the denominator, this term I over c, I can call that a section modulus. So the idea behind a section modulus is really just to simplify some calculations. It's sort of just a shortcut. So, for example, if I have axial stress, the formula for axial stress is P over A, an applied load divided by an area, a cross-sectional area. And so the idea behind this is we can have an applied moment divided by a similar property. So if it's P over A, now it's M over S, and S being the section modulus. Okay? And so we can look these values up for I sections. We can look up an I value, an S value, and an R value. Okay? In fact, let me just sort of make sure that we're all on the same page. So just to sort of like orient everybody to what I'm talking about here. So, for example, if I look at table 1-1 and I'm looking at W shapes and whatnot, and I look over here on the right page and I see, for example, this is the x-axis and the y-axis, you can see we have a moment of inertia, we have a section modulus, we have a radius of gyration. A moment of inertia, section modulus, radius of gyration. That's what all these terms are. What we haven't talked about yet is this term Z, and that's what we're going to sort of illuminate today, is what is Z, how does it apply to bending, and so on and so forth. So we're getting there. That's going to be a main, if there was a, what was it, like on Sesame Street, like this lecture is brought to you by the letter Z. So that's sort of what we're doing here. Okay, we'll get to that. Okay, all right, so let's go back and rewind the clock a little bit to Engineering 216. And sigma equals my over I, or sigma equals m over s, is the expression that we use to characterize bending stresses. And so what we do in Engineering 216 is we might say, I'll tell you what, if sigma equals m over s, maybe what we'll do is say, okay, for a given material, what is the biggest sigma that we will allow? What is the biggest stress that we will allow? And since Engineering 216 largely assumes linear elastic behavior in the mechanics-based calculations, we'll say, I'll tell you what, let's limit the stresses to Fy. That's our biggest sigma. Sigma max equals Fy. So elastic bending theory is going to hold true until that's the case. And so what we'll do is we'll say, all right, if the sigma equals Fy, set that equal to m over s, what we can then figure out is what is the biggest moment that we can apply to a cross-section. And that biggest moment is, in this case, we'll call my. And that biggest moment is, again, assuming elastic bending theory. Okay? So I'm rattling on a little bit, but I want to take a step back and make sure that I'm precise and clear in what I'm saying. What I am saying is that if you restrain your analysis to elastic bending theory, then I propose the yield moment, or the point at which the stress at the extreme fibers hits Fy, that is the largest moment that the beam can withstand if you restrict your beam's behavior to elastic bending. But I guess a follow-up question to that is that actually the largest moment that a beam can withstand? And my answer to that question is no. Okay? So, does that make sense? Everybody with me on that? Now, I'm using this term elastic bending theory. Let's just sort of make sure that we're clear on that. So what elastic bending theory means is that the beam essentially behaves like a rubber band, okay? So I load the beam deforms. When I take the load off, it snaps back to, or returns back to its original state with no permanent deformations applied. Okay, that's what elastic bending theory means. And so what the yield moment is saying is that I'm bending, and so that stress profile is increasing until either the top or the bottom reaches Fy. Okay, and that is true. That's when elastic bending theory would sort of break down, because then we've hit Fy on the top and bottom, and then we're going to start to lock in permanent stresses. But then the question is, well, what happens past that? We're going to get to that. I want to take a step back and go through some engineering 216 calculations with you. Now, I want to be crystal clear. You are not going to have to do these calculations in this class, okay? This set of slides on this example is really more meant as a refresher, okay? And I also want to use this symmetric example to sort of explain not only what S is, but what Z is. And so we'll get to that here in a bit. Okay, so I have here an I-shaped cross-section. I'm trying to keep the cross-section really easy. So I've said that every plate is 1 inch thick, okay? In all honesty, we would probably never design a cross-section like this, except for maybe if it was a built-up section and maybe a high-rise building, and so you had this one column that's going to see a ridiculous amount of load. In that case, yeah, you'd probably have a section like this. But in most routine practical applications, we never use something like this. But again, trying to keep the math a little simple. So just to make sure we're all on the same page, this is a 12 by 1 top and bottom flange. The web is 24 by 1 inches. Okay, so just to make sure we're precise on some things, the total height of the cross section is 26 inches because it's 24 and then 2 plates on the top and bottom. Okay. The other thing is, so remember that term extreme fiber distance from the centroid to the very, very top or the very, very bottom. Okay. Without calculating the location of the centroid, do we all agree the centroid's running right through the middle of this? It's symmetric, right? It's the same picture up here that it is up here. Okay, so the extreme fiber distance, the CD distance, from the from the centroid to either the very tippy top or the very, very, very bottom is going to be 13 inches or half that. Okay, everybody with me on that? Okay, so a lot of stuff here on this slide. I'm not making you do this by hand, but a lot of stuff here on this slide. I want to digest this a little bit, so let's take our time with this. Okay, so okay. I don't know how you learn how to compute a moment of inertia, maybe in 216. I know how I teach you how to do it in statics. I'm an engineer. I love things in tables, so that's how I do it. So what I'll do is I'll say, okay, let's walk through this calculation. So I have a big table. First thing I'll do is I'll list the shape, right? So I've got the top flange, web, and the bottom flange. Then the next thing I'll do is for each shape, I'll list the area. Remember, everything is 12 by 1, right? So, or 24 by 1. The thicknesses are 1 inch. So this is 12 square inches, 24 square inches, 12 square inches. So I also have here a sum row at the bottom, and the sum is 48. Everybody with me on that? Okay. Now what about this column right here? Okay. Now, I am doing this the long way, and I would argue that for this problem, this is a little bit overkill, but I sort of like showing you this way because whenever the shape gets non-symmetric, suddenly this becomes a lot more relevant. But just bear with me. All right, so the next thing we need to compute are these y distances. And so what I'll do is I'll define a common reference axis. I tend to call that a datum. And basically what I'll do is I'll say from the datum, how far is it from the datum to the centroid of each of these individual shapes. So for the bottom flange, from the datum to here, it's only a half an inch, right? For the web, it's an inch plus half that, so 12 is 13. And then for the top flange, we have 1, 24 and a half, so 25 and a half inches. All right, does that make sense? So if I have A, I have Y, I do AY, so this times this is that, this times this is that, this times this is that, so you can see 12 times a half is 0.6, so on and so forth. Sum that up, I get 624. So this section of the table right here, these first three columns are intended for centroid computations, right? So that divided by that up here tells me the centroid is 13 inches. Now again, we knew that going into this, so this is a little bit overkill for this problem, but again, when the problem gets non-symmetric, that formality is not a formality. Okay, so far so good? All right. Now, to calculate the moment of inertia of this thing, we need the moment of inertia of each individual shape. What's the moment of inertia of a rectangle? Anybody remember that formula? I'll get BH cubed over something. 12. For the center of a rectangle, the moment of inertia is BH cubed over 12. Okay? So, for this, let's take this bottom flange right here. So, it's the width is 12, so it's 12 times 1 cubed over 12. The base times the height cubed. So 12 times 1 cubed over 12 is 1. That's why these two are 1. But for the web, it's 1 times 24 cubed over 12. So that's why the web is so big and the top flange and the bottom flange are so tiny. Okay? Make sense? Now, ultimately, what we're doing is we're applying the parallel axis theorem. Parallel axis theorem states that if you want the moment of inertia of a composite shape, you take the moment of inertia of each individual shape, add AD squared, and if you sum these up, that's the answer. Now, what's AD squared? Well, A is this for each shape. What about D? D is the distance from the centroid of each individual shape to the centroid of the whole thing. So it's actually a really easy calculation. You just take this minus that, this minus that, this minus that. Now, it actually doesn't matter which direction that you do the subtraction in. Like, you could take y minus y bar, or you could take y bar minus y. It really doesn't matter, because ultimately you're taking these d terms and you're squaring it. So it doesn't matter what direction you do the computation in. And so I plus AD squared, we get a term for the top flange web and the bottom flange. Sum it up. The moment of inertia is 49.04 inches to the fourth. I imagine everybody in here has done a problem like this. Am I correct? Okay, good. So this isn't like, this is just refresher, right? Okay, good. So if I wanted to compute, let's say, the yield moment, what I would do is I'd say, okay, here's the moment of inertia. I would take, excuse me, the moment of inertia divided by the extreme fiber distance to get this term right here, which I'll call the section modulus. Take the section modulus, multiply it by, let's say, 50 KSI, if that's the yield stress. So 50 KSI times this gives me an answer. Be cognizant of your units, because this is KSI in inches to the third. I'm calculating a moment, so this comes out in inch kips. So if I want foot kips, I got to divide by 12. Okay? So I get a yield moment of 1571.8 foot kips. That is the maximum amount of moment that I can place on this section before I get yielding at the very, very top or the very, very bottom. Okay? Does that make sense? All right, any questions on that? Now, I posit my question again. Is this the largest moment that the beam can withstand? Can it withstand more moment than this? So let's just, I'm stating the question different ways. Let's just do this. Is this the largest moment the beam can withstand? No. The beam can withstand much more. And this is the reason why. Okay? The yield moment, so let's just look at this pictorially. So the yield moment, this is the yield moment right here. Okay? So what happens with the yield moment is we start off with zero bending stress, and then as we apply moment, we get more and more bending, more and more bending. And then once the very, very top or the very, very bottom hits Fy, that's the yield moment. Okay? But the reason why that's not the largest moment that the beam can withstand is this part of the beam has yielded. What about right here? Has this yielded? What about right here? What about right here? So what the question then would happen is, what if I just, so I've got the beam here in front of me, right? And I'm putting load on it, I'm putting load on it, I'm putting load on it, and then I hit My. So maybe the question is, what if I keep putting load on it? Just keep putting more, keep putting more. What's going to happen is So as we start going like this, what's going to happen is this is the maximum stress. So as we keep applying moment, the yielding is going to penetrate through the cross section until we hit this point. Okay, this point is when every point in the cross section is yielded. So I propose that the yield moment is when we just start to hit Fy at the top and bottom. But this moment over here is when the yield moment is, or when the yield stress is everywhere. Okay? And if we term this the yield moment, this is what we call the plastic moment. This right here, this is what we're going to define as the maximum moment a beam can withstand. Okay? It's when the entire cross section has hit Fy. Okay? Does that make sense? So that is MP. That's going to be our maximum usable moment for a beam in steel design. Okay. Now, some of you might be thinking that seems harder. That seems more difficult to do the math for. But I would argue that computing MP is actually a lot easier than what we just did to compute MY. I think MY is a harder calculation. MP is a lot more straightforward. Because MP, all we're basically doing is summing moments about the central axis. Let me ask a question. How many of you in here have already had concrete design? I am just curious. Is there anybody in here that's already had concrete design? So for those of you that do, you would know that for a singly reinforced beam, what do? We assume the concrete reaches 0.85 FC prime in compression. We assume the steel is ASFY. We find that magic distance A such that C equals T, and then we sum moments. Same idea here. The only difference is we don't have concrete and steel, we have just steel. Okay? So it's the same idea. So for those of you who are planning, I imagine many of you are planning on taking concrete next semester. For those of you that are planning on taking concrete next semester, one of the very first things you'll do in the class is learn how to compute the capacity of a singly reinforced concrete beam. And the way that you do that is pretty much this, only with concrete you have to deal with two different materials. You have to deal with concrete and steel. Here it's just steel. And that doesn't just make the computation a little bit easier, it actually affords us a shortcut. Okay? So the way that we compute MP is we're basically summing forces times moment arms. Okay? But those forces are all going to be computed as the area of a plate in question, or the area of a particular component in question times Fy. So if I wanted to calculate the plastic moment, it would be the sum of moments, which would just be force times distance. But if we look at this expression right here, I can factor out Fy. Okay? I can't really do that in concrete design because I have the concrete is reaching 0.85 FC prime and the steel's reaching Fy, so it's different stress limits for different materials. But if the section is all made out of the same material, I can factor out that Fy. And if I factor out that Fy of this term, I'm left with the sum of AI times Yi. Okay? And the reason why that's special is because that is solely a definition of the section's geometry. Okay? So in other words, that's a section property, and it's no different categorically than a centroid or a cross-sectional area or a flange width. I can pre-calculate a Zx. In this case, we're going to call it Z. I can pre-calculate a Z value for any cross-section and have those tabulated. So what is Zx? Zx is what we call the plastic section modules. And I should say we have a Zx and a Zy, but Zx is far more utilized in steel beam design, so that's why I'll probably just use the term Zx quite a bit. But all Z is a calculation of areas times distances. Okay? So just to walk you through how you would compute Zx, Zx is really, really easy. Let's go back to the symmetric beam design. So in the symmetric beam design, we got that the S value, this is what we got for S, and this is what we got for My. Okay? So how do we compute Z? Well, the first thing we have to do is we have to figure out the line where the area above equals the area below. Okay? Why is that important? Because, again, what we're going to do is we're going to take those areas and theoretically multiply them by a yield stress to get a force. Okay? So we have to find the magic line where the force above equals the force below, or the force in compression equals the force in tension, because the beam can't really run away from you, right? So that axis needs to be found. Now, in the case of a beam that's symmetric, well, that's just the same place where the centroid is, okay? So this line, the area above equals the area below. Some of you might be thinking, well, wait a minute, isn't that always the case? Isn't the line where the area above equals the area below the same thing as the centroid? The answer is no. That is not always the case. I'm going to show you an example today where that happens. But once we find that line, all we do is take areas times moment arms. So for example, the top flange, we take this area, 12 times 1, times that moment arm. So 12 and a half. So 12 times 12 and a half. What about the upper web portion? The area of this rectangle is 12. And how far is it from this line to the center of that web? 6 inches, right? So do that for this, for this, for that, for that. We get that's the Z value. Take Z times Fy. There's MP. It's a lot easier than the S calculation. A lot easier. So a couple observations. I do think Z is much easier to compute than S. And the other thing is that Z has to be bigger than S, okay? Because so what is the difference between MY and MP? See, MP's got to be bigger than MY because MP is what happens when you hit FMY and you keep adding load, right? So this has got to be bigger. And if MP's got to be bigger than MY, Z's got to be bigger than S. Okay? Otherwise, it wouldn't make any sense. Okay? And that is the case for every W section you find in the manual. Okay. Now, everything that I put on the slide here is good, great, grand, and wonderful for symmetric cross sections. But what about sections that are non-symmetric? Okay. I want to introduce some terminology to you, and so what I'm going to introduce is what's called the elastic neutral axis and the plastic neutral axis. Okay. And the difference between the two is the elastic neutral axis is where the centroid is. But the plastic neutral axis is that magic line that splits the section up into equal areas. Okay? In other words, the area on top equals the area on the bottom. Okay? That is not always the same case, but and I'm going to show you an example actually here in a second where that's not the case. But again, throwing that out there just to make it make sense. Let's do an example because I think the example is going to sink this in a little bit more clearly. So, okay, got a little bigger. Okay, so I want to compute ZX for this shape. Okay. Now, I've added a little bit more resolution to the numbers, so we've got different values and different thicknesses and different plate widths, so that as we do the problem, we'll have a little bit more tethering to what we're doing. But it's not symmetric. In other words, the top flange and the bottom flange are not the same size. Is that common in the real world in bridge engineering? You bet. Okay, it is very common that you have different size flanges for fabricated plate girders. That's very common. In fact, it's probably more common than the alternative, with them being the same size. Now, in order to compute ZX and ultimately MP, the first thing that we have to do is we have to find the spot. We have to find some line, like right here, where the area on top equals the area on the bottom. Okay. Find the location of the P&A. Okay. I'm going to draw this again, so bear with me. Okay. So this is 18 by 1.25. Now this right here, this thickness is 5/8 of an inch thick. And by the way, I should mention that for this example, I may be a little bit fast and loose with actually writing the unit symbol on every single calculation, especially because I'm going to be writing some formulas. But everything's in inches for the ZX computations. That part shouldn't be that big of a deal. Okay. Now, what I'm trying to do is find this line. And I'm trying to find this line such the area on top equals the area on the bottom. Now, I don't know where that line is, okay? So algebra tells me that when I don't know something, maybe I'll call it x, okay? Now, if that dimension is x, okay, I'm going to move this 5/8 over. If I don't know something, I call it x. If that dimension is x, what is this dimension right here?
32 minus x.
32 minus x. Okay. So let's see if we can write a formula for the area above and the area below. So we'll call this area of the top. Okay, and so what is this going to equal? This is going to equal 14 times 0.75 plus, and then it's going to equal that times that, right? So, excuse me, do a little bit of algebra. 14 times 3/4, that's going to be 10.5 plus, and then how do we do this? We have to do 5/8 times this and 5/8 times that, right? So this is going to be 5/8 of 32, which is 20, minus, and so that's going to be that, right? Is that fair? Yes.
And the 5/8 times 32 minus x is just the area of the web above the line.
Above the line, yes. So that times that, which is that distance. Now for the bottom, call that area sub bottom. So what am I going to do for this? You tell me.
18 times 1.25.
Okay. Plus
X times 5/8.
So 18 times 1 1/4, that ends up being 22.5 plus 0.625x. Does that make sense? So therefore, the area on top has got to equal the area on the bottom. Okay? So 30.5 minus 0.625x equals, I'm going to scroll that up just a bit. Okay. I don't like dealing with negatives if I can avoid it, so I'm going to add that on either end, okay? That's going to cancel that, right? Then what I'll do is subtract that. So that cancels. And so on the left, I'm going to get 30.5 minus 22.5. So what is that, just 8? And then I'm going to get this, right? Because this is 5/8 plus 5/8, so that's 10/8 or 5/4 or 1.25, right? So that means x equals what?
6.4.
Okay. So, okay. So x equals 6.4. So let's go ahead and indicate that right here. So this is x equals 6.4. And then 32 minus x. What is 32 minus 6.4? What is that? 25.6. Okay. We'll do that. Okay, does that make sense? Is everybody able to sort of discern the areas, or sorry, the how we did that? I hope so, because I've got a problem due Wednesday for this very reason. Okay, everybody good? Okay, now, to compute zx, okay, I'm a numbers guy, so I'm going to number this. So I'll just say 1, 2, 3, 4, right? Everybody see what I'm doing here? So okay. All right, so I'm probably going to need your help a little bit here. I'm going to try and not scroll too much. We know the area of shape 1 and shape 4. Shape 1 is 10.5. Shape 4 is 22.5 because we did that. Okay? So help me out. What is the area of shape 2? So it's going to be 25.6 times 5/8. What is that? Okay, what about this one? 4. Okay, so, all right. So if that's the case, so would this be fair? Would that be fair? By the way, what is the sum of these two?
26.5.
What's the sum of these two? So did we find the line where the area up top equals the area bottom? See? So, nice little check. Okay. All right, so I'm going to try and not scroll up and down too much. So let's start with shape 1. So if I were to go up 25.6 plus half that thickness, what would I be at? I'm going to steal a marker. So if I were to go out, so we'll say 1, 2, 3, 4. So if I were to go up, so for shape 1, how far is it from the P and A to the center of shape 1? So I go up 25.6 plus half of that thickness. What is that? What is it?
25.975.
25.975. How about shape 2, how far is it from the PNA to the center of that shape? It's just going to be half of 25.6, right?
12.8.
So 12.8. I think I can do shape 3 in my head, because if that's 6.4, half that's going to be 3.2. Then shape 4, so it's going to be what? 6.4 plus half that thickness, right? So what is that? That is
7.025.
7.025. Is that okay? Did I do that too fast, or is everybody with me on that? So 25, so here I'll scratch it down here on the screen. So this is and this is 12.8. I know that marker was kind of dying on us a little bit, so, but does that make sense? Is everybody with me on that? So now what I'm going to do, remember, it's essentially force times moment arm, but instead of force times moment arm, it's really area times moment arm. So for each row, I'm just going to say, okay, what is this times this, this times this, this times this, this times this. And I'm sure that you all can do that one on your own. So I've got 272.74. I've got 204.8, 12.8, 158.06. So if I sum that, I get 648.4. So in other words, that's my answer. Okay? And by the way, to compute MP, just multiply that times 50 KSI. But by the way, if you do that, this is going to be KSI times inches to the third, so the units are going to be inch kips. So I'm going to divide by 12 to get it in foot kips. And this is there's that. I do have like a couple things I want to show you on the slide. I know we're getting short on time, but before I go down the rabbit hole on that, does anybody have any questions on this? How's everybody doing so far? Is this making sense? All right. I'm going to give you a problem on this type of topic on today, due Wednesday, but I just want to show you a couple things in the slides. So first off, if you take this problem and you go through and you compute it like we did before, like trying to compute IX and SX and all that. So a couple things to point out. The first thing that I love pointing out is this, okay? The centroid calculation is computed as the sum of AY over the sum of A. It is a weighted average, but a weighted average is not the same thing as the line where the area above equals the area below. And if I'm inaccurate in that, then this should have been 6.4, or rather 6.4 plus the thickness of the bottom flange, and it's not. As yielding propagates throughout the section, the axis has to shift to maintain equilibrium. So the axis actually goes down from elastic to plastic in order to maintain equilibrium. That's why that's different, okay? And if you go through and chug it out, you will find that this is MP and this is MY. And the way that you calculate MY when the section is non-symmetric is you calculate an SX for the top and SX for the bottom, and just take the smaller of the two, okay? And again, it's lower. So just some final observations. When the beam is symmetric, the ENA and the PNA are at the same location. You only get one S value, and again, MP is larger than MY. When it's not symmetric, that's not the case, and MP is still larger than MY though. The other thing I like to point out, do you remember a long time ago I said, like for example, when you were looking at angles, I said, look up this quantity, but don't look up this one? Remember I said that? This is the location of the centroid. This is the location of the plastic neutral axis. They're not in the same spot. That's why I didn't want you to look it up. And I told you, I said, just trust me, we'll get there. Well, we got there. So yeah. Okay. Sound good? Yes. All right. I'm going to pull up the code one more time. I'll see you all on Wednesday.